Hello, can you see the screen? Can anybody reply? Hello. Hello. Is there any technical issue? If it is, then I will once again share my screen. I am not getting a response.
Hello, sir. Now it is okay. No problem. You can start it.
Okay, thank you very much.
Okay, sir. Thank
So,
you.
good morning to all of you in this international web conference on advanced nanostructure materials for energy generation, storage, and smart materials, smart applications, being organized by Agricultural Development Trust, Baramati, College, Shardabai Pawar Mahila Mahavidyalaya, Shardanagar. First of all, let me thank the visionary secretary, Mrs. Sunanda Pawar Vaini, for interesting me this opportunity to deliver a talk, of course, via the principal, convener, and coordinator of the conferences. So I take this opportunity to thank Sunanda Vaini for giving me this honor. I am also thankful to Professor R.B. Deshmukh, principal, and Dr. H.G. Sate, who has been principal and convener of this conference. And of course, a very important person of this conference, Dr. T.P. Guzar. If you have a look at the list of the resource persons of these conferences, you will see that the visionary and very dynamic leader who has been in the Shivaji University Kolhapur, Datta, Habib, Ajay, Deepak, myself, all these are the branches of these trees, and we have grown under this tree. Of course, this event has been made possible by the sustained efforts by the coordinator of this conference, Tanaji Guzar. So I take this opportunity to thank all the organizers and my colleagues. Friends, as was introduced initially by my student, Dr. Devkate, I will be talking on photoelectrochemical solar energy harvesting using metal oxide thin films. But let me introduce the institute to which I belong. I am working as a professor in Department of Physics of Shivaji University Kolhapur. Also, I am working as a head and coordinator at the SAIP Center, DST SAIP Center of Shivaji University Kolhapur. You might be seeing on the slides a very greenery and colorful and in rich biodiversity rich the campus of Shivaji University Kolhapur. Shivaji University Kolhapur is situated in the southwest corner of the Maharashtra state. Since last 25 years of career in material science research, I am working on both bulk materials and thin film materials. And I have worked on the various materials like porous ultrasilica, ultralight silica aerosols. Hello? Hello? Okay, thank you. Porous ultralight silica aerosols, composite oxide magnetic materials for EMIC applications, and chalcogenides and transparent conducting oxide materials which were prepared by very economical green chemical routes for energy harvesting, conversion, and storage devices. And the devices which we are investigating, trying, are the solar cell, gas sensors, catalysis, photodetectors, and memory store devices. So my research and the topic on which I am going to talk is related to the materials and material science, of course. This is a very broad and wide field of knowledge, and it has put a foundation stone of modern technological society. As you can see from the slide, it is an interdisciplinary subject underlying the understanding and utilization of properties of matter through various subjects like physics, chemistry, biology, computational engineering, civil engineering, chemical engineering, electronic engineering, etc. So far as research in material science is concerned, there are various challenges, major challenges. These challenges, they are the environmental issues, security issues, health and welfare issues, transportation issues, infrastructure issues, and the energy issues. These are not actually the issues what you can say, but you can call them as the uphill task in front of all of us, because we need to see the pollution problems, we need to see the security issues of the country and health. We are passing through the pandemic, and we need to address this issue by doing the research in material science. Transportation, it should be very safe, very accurate. We need to increase our infrastructure, and that can be infrastructural facilities that can be done with the help of the constant efforts in research in material science. The topic which I am going to address today is the harnessing and utilization of the energy which is abundantly available in the nature. That is the solar energy. We know solar energy. On Earth, we receive the electromagnetic radiation from the sun in the form of visible, ultraviolet, and infrared. We know the amount of visible radiation is 44%, IR radiation is 52%, UV radiation is less than 3%. And these IR radiations, they are utilized for solar thermal conversion. Visible radiations, they are utilized for solar energy photoconversion via solar cell, by making use of semiconductors solar cell. And this solar photoconversion is also used in the photochemical process. We can use electromagnetic radiation to happen chemical reaction, and this photochemical process can be further divided into biological process and non-biological process. And these non-biological process, this best example of a biological photochemical process is the photosynthesis, production of food of the plants. But the example of non-biological process, they are photogalvanic effect, then photochemical effect, and photochemical and photocatalytic effect. So my today's lecture is aimed at seeing application of solar energy in photochemical and photocatalytic processes. To the mankind, there are variety of materials. There has been the list of more than 3 lakhs. And materials, they can be natural materials like wood, or they can be man-made materials like the plastic. Of course, these materials, they are extensively studied, and the list is huge, starting from magnetic materials, superconductor, thermoelectric materials, supercapacitors, electronic materials, biomaterials, graphene, polymers, composite, nanomaterials, optical and photonic materials. So today's lecture is focused on use of semiconductor nanomaterials for energy harvesting purpose. And this we will do by making use of a thin film. This thin film is a well-known aspect. Anything which extends in 2 dimensions and its 3rd dimension, if it is restricted and its dimension is less than 1 micrometer, for example, then we call it as a thin film. And this thin film is supported on the substrate. We cannot work with thin film without substrate. And this thin film technology, it has achieved many technological breakthroughs in various areas like recording media, semiconductor devices, light emitting diodes, optical coatings, hard coating tools, energy generation, energy storage, and pharmaceuticals. In our electrochemical materials research laboratory, uh, various research field includes the utilization of these thin films to see the applications in solar cell, UV detectors, gas sensors, memory stir, transparent conducting oxides, and photocatalysis. And today, I will explain the use of these transparent conducting oxide thin films in photocatalysis. These transparent conducting oxides, thin films, they are very important and crucial materials because they are transparent to the visible light and they are electrically conducting. We know if the material is highly transparent, it can't be conducting and vice versa. But by tuning the material properties, we can achieve the both properties simultaneously, transparency as well as conductivity. And these transparent conducting oxides, if they are deposited on the transparent substrates, they have very attractive applications, very more applications in modern fields like thin film transistors, then ultraviolet light emitting diodes, flexible light LCD screen, transparent screens, defrosters, flat panel displays, and touch panel displays, solar cells, and the photocatalysis. So we are going to use, or I'm going to tell you the use of these transparent conducting oxide thin films in photocatalysis. What after all, before defining what the photocatalysis is, what the catalysis is, let me tell you few applications of the photocatalysis. Then you will come to know the crucial role of this photocatalysis in modern material science research. We can use the photocatalysis reactions for water treatment. We can remove biological, we can remove chemical impurities, we can degrade the chemical impurities in the organic impurities in the water. We can remove the metal traces which are hazardous with the help of heterogeneous photocatalysis, with the help of photocatalysis. We can split water. H2O can be split into hydrogen and oxygen. And for hydrogen production, this photocatalysis process can be used. We know the TiO2 has its own inherent property of self-cleaning. We know the water droplet on the lotus leaf, it immediately rolls on from the leaf because it has the self-cleaning function. So TiO2, if the material surface is coated with TiO2, it acts as a self-cleaning material. It is used in the anti-fogging where humid humid air and hydrophilic surfaces are there. They are used in the antibacterial and cancer treatment. Photocatalysis is used in the antibacterial property or the use where the bacteria, fungi, algae, viruses, and even cancer cells can be killed. And the cell decomposes these materials, the photocatalyst, few photocatalysts, they decompose the dirt and pathogenic organisms, and therefore they are used in the self-sterilization application. So such a important area photocatalysis is. So let us begin by defining what the catalysis is and what the photocatalysis means. The catalysis means to degrade, to disintegrate a chemical material, or we increase the rate of the chemical reaction with the help of some medium called as catalyst. And if this reaction or the catalytic reaction, if it is carried out with the help of a light absorption, electromagnetic radiation, then it is called as photocatalysis. Can we use this photocatalysis for removing the impurities in drinking water? And this has been very enormous and important topic of the recent. Of course, water chlorination, sedimentation is natural or artificial. And what are the byproducts? Byproducts of the photocatalysis, they are harmless, which are carbon dioxide and water. So photocatalysis can be used in water treatment. That's what I mean. What are advantages? As I mentioned, harmless byproduct, hazardous compounds can be disintegrated, mild reaction conditions, and modest time. You don't need very extensive chemical reactions or the reaction conditions. Secondary waste generation is minimal. We can produce hydrogen, and this photocatalysis can be a replacement for energy intensive methods. So photocatalysis is done with the help of catalyst, and the catalyst, it can be a solid. We cannot take liquid or gas or other states of the material as the catalyst. So we can take solid material as a photocatalyst, and we have three options: metal, semiconductor, or insulator. We know in case of a metal, only oxidation and reduction is possible. What is oxidation? Oxidation is giving electron. So this first process, A process, is only exchange of electron, no exchange of hole. If it is a semiconductor, for example, if there is exchange of only hole, then it is reduction, no exchange of electron. If there is exchange of nothing, no reaction occurs, no catalysis occurs. But if there is a simultaneous exchange of electron and hole, there is a simultaneous occurrence of oxidation and reduction, then it is called as catalysis. And this is possible with the help of semiconductors and insulators. With the help of metals, it is not possible, because either reaction takes place, either reduction or oxidation. But in case of insulator, we know the band gap of this insulator is of the order of, say, 3.5 electron volt, or even greater than that, 4 electron volt or so. It is very difficult to achieve the photocatalysis with the help of the light, which is evidently available in the nature. So the only alternative is to use the semiconductor. If you look at the band positions of the semiconductor, conduction band age and valence band age, then they lie between the oxidation and reduction potential of the water. Therefore, we use semiconductor for the photocatalysis. Let us explain the phenomena of the catalysis with the simple example of semiconductor particle. I have a semiconductor particle where valence band is there, where conduction band is there. And if this semiconductor, which is in the contact with, say, some chemical or the redox chemical, where reduction and reduced and oxidized species are there, the electron donating and electron accepting species are there, ions are there in water, for example. So if you bring this semiconductor in contact with such redox chemical, and if this semiconductor electrolyte junction or the liquid junction, if it is illuminated by the light, if the energy of this light is equal to or greater than the band gap energy of the semiconductor, then the electron in the valence band, it absorbs the photon, goes in the excited state, conduction band, and leaving band the deficiency of the charge hole. So electron hole pair is generated. If this electron hole pair is properly utilized, the electron can be used in the reduction reaction and the hole can be used in the oxidation reaction, so that simultaneous reduction and oxidation can take place. And this is the phenomena of the photocatalysis. But if it is somehow, if you are not able to separate this electron and hole, if you are not able to utilize this electron and hole, they recombine and they produce the heat. And this is the challenge in front of the researchers who are working in the photocatalysis area. If somehow they reduce the recombination rate, then the catalytic efficiency can be increased. And of course, the very highly reactive species like hydroxyl radical, they oxidize solutes, and the holes and electron recombine, thereby limiting the efficiency. What are possible semiconductors which we can use where the band gap of the semiconductor should lie the visible region, because our intention is to use the visible light. It is abundantly available. 44% in the solar radiation is the visible form. So this is the list of the binary, ternary, and quaternary photocatalysts, which are extensively studied by various researchers. So band gap is one criteria. We can choose any material from this list, particularly say tungsten trioxide, indium oxide, titanium dioxide, zinc oxide, tin oxide, vanadium oxide, etc., and ternary oxides from this and quaternary oxides. Keeping in mind the criteria for band positions of semiconductor when it is brought in contact with the aqueous electrolyte at 1 pH. So the idea is the conduction band potential of the semiconductor should be more negative than the reduction reaction. It should be on that side. And the valence band position of the semiconductor, it should be towards more positive side than this oxidation reaction. So if you look at the band positions of the few semiconductors, it is seen that these materials like gallium arsenide, gallium phosphide, iron oxide, tungsten trioxide, tin oxide, they seems to be unsuitable for the water splitting or for catalysis. Cadmium sulfide, cadmium selenide, they are not stable. But the semiconductor like TiO2, zinc oxide, strontium titanate, silicon carbide, they are suitable depending on the band position. But if you suitably tailor the band positions of these iron oxide, tungsten trioxide, and tin oxide, these also can be used as the effective photocatalyst, and we're going to address this issue later. So TiO2 and zinc oxide are the material. Let us discuss the homogeneous photocatalysis or the heterogeneous photocatalysis with the help of powder catalyst, mobile catalysis, where if you want to remove the organic impurities in the polluted water, the catalyst in the powder form is immersed in the polluted water, and this water is continuously stirred and it is being illuminated by the sunlight, and the non-toxic byproducts they are evolved, for example water and carbon dioxide, for example. So this is the simple process of powder photocatalysis, where with the help of TiO2 like zinc oxide photocatalyst, various viruses, odor, bacteria, and algae from the water they can be removed. And what is signature of the first signature of or the first evidence of the purification of water? You just see the absorption spectra of the liquid. So you pass the light and measure the transmittance or absorbance and plot the absorbance with respect to wavelength in the visible light. You will see that you get a peak for corresponding compound in the visible region, and the peak intensity continuously decreases with respect to time, and that is the signature of the degradation. And so this is the example of the powder catalysis. This catalysis, photo generation and photo utilization occurs in two ways. For example, I explained the phenomena of oxidation and simultaneous oxidation and reduction for the single particle. So when single particle is illuminated, electron and hole pair is generated, oxidation takes place here and reduction takes place there. But when you take the material catalyst in the aggregate form, in the huge form, in the bulk form, for example, and if it is aggregated, then if whole surface of the particle it is not in contact with the polluted water, then reduction and oxidation which occurs here, it doesn't occur in the aggregate n-type semiconductor, for example. It happens that one of the particle, it absorbs the photon, electron and hole pair are generated, hole is utilized here for reduction, and electron it goes via the intercrystallite electron transfer process to other crystallite and oxidizes. So this is very important aspect which we need to understand. So TiO2 is extensively studied for photocatalyst. It is well studied. Therefore, we prepared TiO2 powder, and it was observed that this powder was anodized phase. It exhibited anodized phase, and we degraded rhodamine B. This is one of the test pollutant. We took some chemical, organic chemical, and deliberately added this chemical in the pure water. So water become impure. This impure water was made pure by putting the TiO2 powder, which we prepared with the chemical route, and we saw that the continuously it is possible within 40 minutes or so, this impurity rhodamine B is completely removed, or more than 60% is completely removed. But use of this TiO2 is uneconomical due to its cost and its availability. But we can find the suitable alternate to this TiO2, and zinc oxide is one of the suitable alternate, because the photo degradation mechanism in case of zinc oxide is very similar to that of TiO2, and this zinc oxide absorbs large fraction of the solar spectrum. Therefore, we prepared TiO2 via two routes, chemical routes, precipitation and combustion. So it was observed that the zinc oxide, which was prepared by precipitation route and subsequently sintered, it exhibited the polycrystalline nature, or the crystallinity was more. But the crystallite, or the powder prepared with the combustion technique, it exhibited nanocrystalline structure. The theme of this conference is to see the use of nanocrystalline material. What is the advantage of nanocrystalline material in this photocatalysis? That issue also I am going to address, but later on. But here I would like to remind yourself that if we prepare the material in the nanocrystalline size, then the surface area which is available for the catalysis, it increases, particularly this diagram. The surface area, surface to volume ratio of the particle, it increases, and that increases the catalytic efficiency. So you need to prepare the material in nanocrystalline form. And these are the degradation results of the zinc oxide nanopowder. What happens when the photon is absorbed by the semiconductor particle? Then the electron and hole, they passes through various chemical reactions. Of course, I'm not the chemist, but I can explain with the help of absorption of electron, the very highly reactive oxygen species like H2O2, then O2 dot, then OH dot, they are produced, or they are produced, and these in presence of organic pollutant, for example, and the harmless byproduct like carbon dioxide and water, it is produced, and the overall chemical reaction it can be proposed chemical reaction can be. So what is the lesson? Lesson is the mechanism of photocatalysis is when we illuminate semiconductor material in presence of organic pollutant with the help of reactive oxygen species, it is possible to degrade any organic compound, and it is converted into harmless byproduct CO2 and H2O. But this powder catalysis had got some disadvantages, and this is called as the mobile catalysis. Powder catalysis is also called as mobile catalysis because catalyst is moving in water, and the reaction is occurring when it is in motion. It is possible that the catalyst itself get modified in this photocatalytic reaction. If it is moving, if it is mobile, there is possibility of occurrence of irreversible chemical reactions with the byproducts. And of course, when we make use of this catalyst for water purification, it is very difficult to take out this nanocrystalline powder from the purified water, because this nanocrystalline powder, if it is present in the impure water, that itself is the impurity. So very difficult to take out these catalyst from the pure water. Therefore, alternative strategy was suggested to use the bias, electrical bias, DC electrical bias, and to use the electrode system in the polluted water, and to use the photocatalyst in the immobile state, in the heterocatalytic reaction. The reaction occurs at the boundary between liquid and solid. So we need to prepare a material in the thin film form, semiconductor electrode in the thin film form, and deposit on the substrate, and use that substrate or the material deposited on the substrate in the photoelectrochemical solar cell, where there is a provision of giving electrical bias, and there is a provision of illuminating this junction. So what happens if we apply electrical bias? we can enhance the photocatalysis by applying the bias, because there is effective charge separation. The recombination between electron and hole, it can be reduced to greater extent, and we can increase the efficiency of the oxidation. And this is the small schematic diagram of the immobile catalysis, where the catalyst, they are in the form of thin film or the substrate, and the impure water is purged in from here, and there is a provision to illuminate this junction between impure water and photocatalyst, and polluted pure water, it comes from the other end. So this photoelectrocatalysis is the alternate strategy to the powder catalyst. And we can, as I said, we can use photoelectrochemical cell. Photo means photon, electro means we apply electrical bias, chemical means redox. So there are two junctions. One is a semiconductor electrolyte junction, and other is semiconductor metal and electrolyte junction. So now I will not go in the details of the way in which this junction is formed, or the way in which double layer acts, where the way in which oxidation and reduction potentials they are there. But they keep in mind the fact that here, very similar to powder photocatalyst, here also, if the junction between semiconductor and electrolyte, the electrolyte being the polluted water, if it is illuminated by the appropriate light, then electron and hole pair can be generated. Electron, it will follow the external path now, because this end is positively biased. Therefore, it will follow the external path, and it will enter the solution through other end. And hole, it will come, reduction occurs there, and oxidation occurs there, and reduction and oxidation reaction gives rise to disintegration of the impurity in the water. The way in which this electrode, thin film semiconductor electrode can be prepared, it can be prepared by a variety of techniques. There are physical, chemical, biological methods for preparation of the thin films, but here I have mentioned only two, physical and chemical. Physical method, as you know, they are costly, and they have their own disadvantages, and the very huge equipments are needed, and they are time consuming, vacuum is needed. But the chemical methods, particularly liquid phase chemical methods, not gas phase, because gas phase chemical methods also require elevated temperature of the order of 800 to 1000 degrees centigrade. But the liquid phase process, Professor C.D. Lokhande yesterday talked about these chemical methods. As he mentioned, only chemical beaker and chemical and beaker is needed to carry out the deposition. Therefore, with the help of any chemical method, particularly spray pyrolysis, because it has got advantage of preparation of large surface area thin films and well adherent and oxide semiconductor thin films. Therefore, spray pyrolysis is preferred. Of course, these methods I listed, and spray pyrolysis, I also preferred the spray pyrolysis. This is the photograph of the zinc oxide thin films deposited over tin oxide. So in this configuration, where glass, transparent glass, then on that F2 and the zinc oxide, they are deposited. So this electrolyte or this electrode is being used in the PEC cell for purification of water. In this specially designed parallel plate flow in the PEC cell, and of course this cell was designed under the supervision of Professor Michael Newman Spellat, our international collaborator, and under the supervision of respected Professor C.H. Bosley sir. So the photocatalyst is deposited on the transparent conducting oxide. This transparent conducting oxide, it acts as a back contact, because we need to give the bias. So this acts as a back contact, and this has been deposited on the visible transparent substrate, glass substrate, for example. And here I would like to tell you why I was talking of the use of transparent conducting oxide in the photocatalyst. Because if the material, if it is not transparent to visible light, then this light will not go up to the junction, because light needs to reach up to the junction. Once it falls on the junction, then only electron and hole pair will be generated. Therefore, substrate should be transparent. Your transparent conducting oxide, it should be transparent, and of course photocatalyst too. And this parallel plate flow or reactor, if it is connected in series or many cells they are connected in series, then the catalytic or the degradation time can be reduced. Here schematic diagram of the PEC degradation experiment, where the cell connected to the potentiostat, there is a facility to give the illuminate this junction by the light, and there is a facility to continuously have the flow through peristatic pump. As I said, this work and this reactor, it was developed with the under the supervision of Professor Michael Newman Spellar. Hello. Hello. Lecture चालू आहे माझा online. Professor Michael Newman Spellat and Professor C.H. Bosley, under their guidance, our group has developed 9-cell reactor for the photocatalysis, PEC detoxification reactor. This small animation shows, of course, this animation was prepared by our one of the alumni, Praveen Shinde. He himself worked on the photocatalysis. So here the impure water is being pumped in the reactor through peristatic pump, and it has given the bias, and there is a provision of illuminating this material with the help of UV light. If you want to do the experiment with the help of TiO2, then it needs UV light. I'm going to tell you how visible light also can be harnessed. And in the outlet, you get relatively pure water. If this relatively pure water, if it again, if it is purged and if it is circulated for 3 to 4 hours, it is possible to remove any inorganic or any biological impurity from the polluted water. And if these are the results, as I said, you measure the extinction, then the absorption spectrum. So these are the results on one of the test contaminants, salicylic acid. This salicylic acid, when it reacts with highly reactive species like OH dot, it goes through various chain reactions, and it continuously loses the number of carbons, and finally CO2 and H2O is produced, and the peak intensity continuously decreases. The rate constant of the catalysis is very important. It should be very high. When you plot the logarithm of the normalized concentration with respect to time, we get a slope, and that slope is the rate constant, and that rate constant should be high. When rate constant is high, then degradation is fast, and vice versa. These are the results on the salicylic acid, where the chemical oxygen demand, of course, is the chemical oxidation, COD, chemical oxygen demand, is proportional to the amount of organic impurity or organic chemical which is present in the polluted water. So if COD decreases continuously, means amount of organic matter continuously decreases, means it degrades. So it is possible to achieve COD of the order of 6 mg per liter after 6 hours. We know COD of potable water, drinking water, should be less than 10 mg per liter. So it is possible to get potable drinking water out of polluted water with the help of this photocatalysis, photoelectrocatalysis. Of course, in addition to COD, we measure TOC, etc., and standard dichromate method we use for measuring COD. What are various factors on which this photocatalysis depends? Of course, initial solute concentration. It should not be too high or it should not be too low. It should be optimum. Light intensity is same. It should be optimum. It should not be too high, so that photodegradation may occur. It should not be too low, that it should be insufficient to happen the photocatalysis. We don't prefer acidic or basic pH of the solution, because certain materials, they are not chemically stable. TiO2, of course, is chemically stable, but for other semiconductors, the pH should be it should be such that our photocatalyst doesn't get dissolved. And of course, it depends on the temperature. Preferably at higher temperature, degradation rate is high, but there also there is possibility of degradation of the photocatalyst. And of course, the material. Which material, photocatalyst material, its form, whether it is in the form of composite or if it is doped or what. So photocatalyst material also is very important. The way in which photocatalytic impurity can be efficiency can be improved is various ways. Here I have listed few. What we can do, for example, as I said, if TiO2 taken as a photocatalyst, then it is chemically stable. But the energy requirement for using TiO2 photocatalyst, they are high. So we need to use UV light. And in sun radiation, UV light is not in the abundant form. And our cost of detoxification reaction, it increases. So what we do, we make a composite of this TiO2 with other semiconductor in such a way that the UV light is harnessed in TiO2 and visible light is harnessed in visible light. Other semiconductor whose band gap is less than TiO2, and in this way it is possible to improve the photocatalytic efficiency. We can do the photocatalyst by metal or non-metals for monitoring, for degradation, or what you can say, for tailoring the band gap and the positions of the energy levels in the semiconductor to increase the photocatalytic. We can sensitize our photocatalyst either by the oxide or the metals or the dye. Surface modification, oxidation co-catalysis and reduction co-catalysis also is the strategy people they are continuing increasing. And of course, the use of nanocrystalline materials, high surface to volume ratio. This also will improve the photocatalytic efficiency. So to prepare the composite between the various semiconductor, we can choose one semiconductor, high band gap semiconductor from this list. For example, zinc oxide, zirconium oxide, or tin oxide, or titanium dioxide, and make a composite between, say, cadmium selenide, or say iron oxide, or other semiconductor, iron oxide. So how to choose, or what is the criteria to choose? We know if you plot the band gap positions of various semiconductors like zinc oxide, TiO2, tungsten trioxide, iron oxide on the solar radiation spectrum, then it is seen that the band positions of zinc oxide and TiO2, they are in UV. But the band gap of the iron oxide and TiO2, tungsten trioxide is in the visible. So why don't we make a composite between iron oxide and TiO2, or say tungsten trioxide and zinc oxide, in order to achieve the more photocatalytic efficiency? So depending on the band positions, whether it is straddling type of heterostructure or staggered type heterostructure or broken gap type of structure. So depending on the band positions of two semiconductors, high band gap semiconductor and low band gap semiconductor, these various heterostructures they occur. Generally, we prefer the second type of heterostructure, staggered type of heterostructure, where the band position or the valence band of one semiconductor is between the band gap of other semiconductor, and conduction band is above the conduction band of other. So here I have showed the example of making the heterojunction between two semiconductor, one high band gap semiconductor, low band gap. Of course, they have suggested the heterostructure between three semiconductor also, by making use of this staggered gap type of mechanism. People are using the nanotechnology to improve the photocatalytic efficiency. Here, the example of making use of cadmium sulfide TiO2 nanocomposite for photocatalysis is schematically shown, where the cadmium sulfide quantum dots, they are sensitized and TiO2 nanorods. And these TiO2 nanorods, they are grown vertically upward out to the substrate surface. So this is the band position, and it is possible to improve the photocatalytic efficiency. The main aim is to avoid the recombination of electron and hole. People are making composite between composites. So this is Ag doped CuO, and if you make composite between Ag doped CuO with the TiO2, this is the corresponding team image. Then also people have reported the higher photocatalytic efficiency. We, in our one of the major projects, made the composite of iron oxide with TiO2, where the band positions of iron oxide and TiO2 are shown. This is the first type of heterojunction, and the band bending gives you the potential and depletion potential, and UV is harnessed in TiO2 and visible is harnessed in iron oxide, and thereby increasing the photocatalytic efficiency. We have made the composite of TiO2 and gallium doped tungsten trioxide also. So this is the IV diagram in the photocatalytic experiment. For pure WO3, the current is less. For gallium doped tungsten trioxide, current increases, and for the composite between TiO2 and gallium doped tungsten still increases. So here you can see the contribution of making composite between various semiconductors. It is possible to tailor the band gap of a material by doping this material either by pure metal or by the non-metal. So the possible dopants, they are iron, platinum, Mn, Cr, B, Ni, Ag, N. We have tried these for zinc oxide, metal and non-metal dopants, to reduce the recombination rate and to reduce the band gap energy. And of course, we deliberately put in the impurity levels between the band gap. So if this is the situation, band-to-band transition for the pure TiO2, if it is doped with the metal, then the band positions are reduced, and if it is doped with the non-metal, the band positions, they are like this. So it is possible to tailor the band positions and to harness more visible light by making the material more efficient. As I told, we have used nitrogen, Ag, lithium, UBM, Au for doping in zinc oxide, tungsten trioxide, and TiO2. And you can see the rate constant. Rate constant, if it is high, the photocatalytic efficiency is more. So in case of Ag doped zinc oxide, we achieved highest rate constant. And it is possible to improve the photocatalytic efficiency. We can sensitize the semiconductor surface with the help of a proper dye, because we know the dye, they are colorful and we can see their color because they absorb the visible light. The best examples of the dye are acid red 44, eosin Y, membrane, rhodamine B, rhodamine 6Z, etc., etc., etc. So basic concept is to have the junction between dye also is a chemical, and the other semiconductor, where we reduce the recombination of the electron and hole. People use the heterojunction between the composite between the organic and inorganic. I'm going to tell you this soon. So the use of the composite between graphene and metal oxide is schematically illustrated here. We can modify the surface by reduction co-catalyst and oxidation co-catalyst. So we can attach to the surface of the catalyst the co-catalyst, like this is semiconductor, and to this semiconductor particle co-catalyst is attached, and it is possible to trap the electron by reduction co-catalyst, and it is possible to accept the hole with the help of oxidation co-catalyst, and thereby increasing surface passivation and increasing the photocatalytic efficiency. So we can improve the surface recombination by making use of oxidation and reduction co-catalyst. I'm not going to explain you in details the way in which this recombination is avoided. It is possible to degrade the textile effluent. We collected the outlet of one of the textile industry. We serially diluted that outlet water, and it was possible to remove textile or the impurities which are present in the textile effluent. We collected the samples from the sugarcane factory wastewater. It was possible for us to remove the impurities, of course, after serial dilution, to remove the impurities in the sugarcane waste or factory wastewater. It is possible to remove the biological impurities with the help of antibacterial effects of the photocatalyst. If we embed our thin film, a polymer, for example, in the liquid where bacteria are present, then it is possible to destruct or remove the walls. It is possible to remove the walls of SRS bacteria, for example. Here it is demonstrated with the help of the configuration like on glass substrate, polymer film is deposited, and on that doped TiO2 thin film is used. In our case, we have used zinc oxide for degradation of E. coli bacteria, and after maybe 2 hours or so, it was possible to remove the whole bacteria, E. coli bacteria. We have worked on various systems in our ECML and 2 review articles based on this topic. Those who are interested to work in this photocatalysis, they can refer to these review articles, which one was published long back. And now currently in this pandemic situation, we once again publish one more review article in current applied physics. And this is the list of the system which we have studied: benzoic acid, MO, toluene, salicylic acid, 4-CP, oxalic acid, MB, AO7, eosin Y, RB, starch, phthalic acid, textile effluent, factory wastewater, E. coli. Even we could disintegrate the seawater. One of the disadvantages of this photocatalysis method is it is not possible. Still, our continuous efforts are centered around to address this issue. It is not possible to remove inorganic impurity. That is another branch of the photocatalysis. But keep in mind, we were able to disintegrate the impurities in the seawater. And this is the list of the papers which were prepared, reported, which were published in last 10 years on the photocatalysis. We have used TiO2, iron oxide, zinc oxide, tungsten trioxide, their composites, their doping, their nanostructures, by a variety of chemical methods. Our current efforts are focused on preparing the ternary oxide thin films like bismuth tungsten oxide in the photocatalysis. And metals and non-metals which are utilized for the photocatalysis is this is the list of the catalyst which is investigated: TiO2, zinc oxide, iron oxide, tungsten trioxide, and these we already tried. And the composite between TiO2 and tungsten trioxide, composite between iron oxide and zinc oxide, and other we have already tried. People, they are working on reduced graphene oxide, then carbon nanotubes, carbon nitride, tungsten sulfide, etc., as well. So research trend and opportunities in this field are concerned, then they can work on the semiconductor like bismuth vanadate. Copper oxide also is nowadays used because it is possible to tailor the band positions of copper oxide, and their band gap of copper oxide lies invisible, and it is relatively chemically stable. And copper itself is the catalytic element. Therefore, the copper oxide is also extensively used. Then carbon nitride, people are investigating hard. So organic semiconductor photocatalysis. So there is a composite between organic semiconductor, organic inorganic semiconductor, inorganic semiconductor. So people they are utilizing or using organic semiconductor photocatalysis for. And this is the contributors. This is the list of the contributors who have worked on photocatalysis in our laboratory. The group headed by respected Professor C.H. Bhosle and our foreign collaborator, Professor Michael Newman-Spelard, Praveen, Sambhaji, Ramchandra, Vijay, Santosh, Yuvraj, Ramchandra, Namrata, and Rupesh are currently working. And this is my research group. I'm very much thankful to all my research students, because without whom this work would not have been possible. So I take this opportunity to thank all of you Hello. Any background noise? Hello.
Hello. Hi, sir. Hello.
I'm very much thankful to all of you for your patience listening.
Thank you. Thank you very much, sir, for giving the very nice explanation.